morning, teams. As part of our ongoing commitment to quality assurance and continuous improvement, we are holding this internal review session to present and discuss our recent findings regarding the output quality of our memory chip production at the Palo Alto, California facility. Our team has been tasked with evaluating the weight consistency of the memory chip, each designed to meet the standard of 3.56 grams as part of our deliverables for the Manned to Mars space mission. Over the past week, we collected data from both morning and afternoon shifts spanning 5 working days. We then applied various quality control tools to identify any non-conformities, trends, or anomalies in the production process. So today, each team member will present your findings based on the analysis tool we are assigned. Let's begin. First, I'd like to invite Christian, who will walk us through the checksheet results. Christian has been monitoring the frequency and type of defects recorded during the production shift. So, you may share your finding, Christian.
Thank you, Mr. Aris. Now I'm going to present on how I analyze the data. For example, on the Monday first shift, I selected the 300 range of data, and from there, the standard weight given is 3.56 gram with 0.1 tolerance. I've combined the defect rate, whereby any value above 3.660 gram and below 3.460 gram will be counted as defect. For example, on the Monday first shift, the defect rate is about 80.67%, while the expected range value of the standard weight of the chip is 19.33%. Next part, I'm going to animate the animation on how to calculate the maximum value, the minimum value, and the range of the data, and then to determine the cell interval, cell midpoint, cell boundary in order to produce the respective table for the chart.
Thank you, Christian. Next, I will present the Pareto chart analysis, which highlights the most significant cause of defects in descending order of occurrence. These tools allow us to focus on the vital few rather than the trivial many. So I will share the Pareto chart here. This is how to construct the Pareto chart. Firstly, we need to take the frequency data, and then we have to sort the data from largest to smallest, so basically in descending order. And then we also need to take cumulative of percentage in percent, and then select both of this data to start inserting a combo chart. Here we have the selection, so we have to select series 2 for this. It's okay. And then we need to arrange and modify this chart according to the data. Conclusion: this chart helps identify which measurement ranges are most frequent and contribute the most to variation. It is useful for prioritizing quality improvement efforts by focusing on the high frequency intervals. Our team should investigate why the first few intervals are dominant and whether they fall within acceptable specification limits. We continue to build or construct the Pareto chart for other days and shifts. That's all from me. Thank you. Next, following that, I'll pass to Mr. Abang Muhammad Azri, who has compiled a histogram to show the distribution of the product's weight.
So, histogram is a graphical presentation of the distribution of numerical data. It helps us to see the frequent data points within specific ranges in order to identify patterns and also outliers. From the 300 data that I gather, every shift from Monday to Friday, first and second shift. So this is the data that I gather. We can see here on Thursday we have the highest frequency of 54. This 54 frequency means that the data falls within the standard range of 3.56 gram. While Tuesday first shift and Friday first shift, it has the lowest of frequency. So it may have a problem with the quality control. So I think that's all for my part. Thank you.
Thank you, Abang Muhammad Azri, for your presentation regarding the histogram. And lastly, Ms. Shania will present the control charts results, which help us determine whether our manufacturing process is operating under statistical control. So the floor is yours.
Thank you, Mr. Iris. So, I'm Ms. Shania, and I'll be demonstrating how to create a control chart, followed by presenting the results for Monday's first shift and the overall process. First, let's go through the steps to construct a control chart. A control chart is a tool used to monitor process stability over time. It concludes data point and a center line for the mean and the upper and lower control limits to detect variation. To begin, we calculate the mean range and range for each subgroup of data. In this case, our sample size is 10. Based on the standard control chart constant, A2 is 0.3080, the D4 is 1.770, the D3 is 0.2230. Next, we use this constant to calculate the control limits. For the X bar chart, we calculate the upper and lower control limits using the formula here. And for the R chart, we use the formula here. After computing all these values, we plot the chart using the subgroup means and ranges. This allows us to visually check for any points outside control limits or patterns indicating instability. Now let's move on to the result. For Monday's first shift, all the data points are within the control limits. There are no outliers or abnormal trends, showing that the process was stable and in control during that period. Looking at the overall data, Monday first shift, Monday second shift, Tuesday first shift, Tuesday second shift, and the others, we see a similar pattern, no special cost variation, and all points are within limits. This confirms that the process is consistently operating under statistical control. In summary, both the Monday first shift and the overall process are stable and performing reliably. Thank you very much.
Alright, thank you all for your thorough presentations. To summarize our collective findings, the check sheets help us categorize and count the different types of effects, showing clear patterns across shifts. The Pareto charts reveal that a majority of the defects are due to a few root causes, which should become our immediate focus area. The histogram demonstrated that while we want a bulk of product weights cluster around the target value, there is noticeable spread suggesting variability in the process. And lastly, the control charts indicate several data points outside of control limits, signaling the presence of special cause variation in some shifts. Based on this analysis, we can conclude that the process is not fully stable and may be influenced by factors such as equipment wear, raw material variation, or operator inconsistency. Do you guys have any ideas on how to overcome the problems?
I would like to recommend a refresher training for shift operators on handling and inspection procedures. This will improve safety, reduce errors, and ensure consistent quality. The section can be brief, but focus on proper material handling, defect checks, and tool inspection.
Thank you for your brilliant idea, Ms. Shania. Anyone else have any ideas for the recommendation?
I too would like to suggest a recommendation. We have to do preventive maintenance. It is a scheduled maintenance activities performed at predetermined intervals. It is to prevent equipment failure and reduce wear and tear. This can minimize quality issues.
Thank you, Mr. Abang Muhammad Azri. So what about you, Mr. Christian?
I would suggest to increase the sampling frequency during critical process windows for tighter monitoring, mainly focus on where the defect usually happens, in order to mitigate the problem and issues encountered.
Thank you, Mr. Christian, for your ideas. So as for me, we have to solve the root cause analysis on major defect types. To conduct a structured root cause analysis such as the 5 whys or fishbone diagram to investigate the top contributors of 2 defects. So I think that is to conclude our internal review session for this morning. Thank you guys for your cooperation today. See you soon.
Thank you.
Bye.